Hi everyone, welcome to Studia Academy Past Paper Walkthrough. In this video, we will be discussing IGCSE Edexcel Physics, May 2024, Paper 1P. First up, question 1 is all about motion in the solar system. For part A, you're asked to draw a labeled diagram showing the moon orbiting the Earth. So you'd sketch the Earth, then the moon in a roughly circular orbit around it, and just label it moon. Simple enough. Moving on to the next part, the question asks for the name of the force causing this orbit, and that's the gravitational force. Remember, this force from the Earth is what acts as the centripetal force on the moon. For the following question, if you need another object that orbits the Earth, you could say an artificial satellite. Finally, for part B, we compare a planet and a comet orbiting a star. The key difference is that a planet typically has a circular orbit, whereas a comet has a highly elliptical orbit. Moving on to question 2, which is all about radioactivity. Part A gives us a carbon nucleus with 6 protons and 8 neutrons, and asks us to identify a different isotope. The key to an isotope is that it has the same number of protons, so it must still be 6, but a different number of neutrons. The correct option, therefore, has 6 protons and 6 neutrons. Part B is straightforward. The type of radiation that is a high-energy electron is a beta particle. Part C is a bit trickier. It describes a nucleus emitting radiation, causing the mass number to decrease by 1 while the atomic number stays the same. If the proton number hasn't changed but the mass has gone down, it must have lost a neutron. So the emission is neutron radiation. For part D, we have a uranium nucleus with 92 protons. To be a positively charged ion, it must have fewer electrons than protons. So we're looking for the option with, say, 90 electrons. And finally, part E deals with half-life. An isotope has an initial activity of 400 becquerels and a half-life of 8 hours. After 16 hours, that's 2 half-lives. So the activity halves from 400 to 200, and then halves again to 100 becquerels. Question 3 shifts our focus to waves, specifically infrared. Part A asks for a harmful effect of infrared waves, and a classic example is that they can cause skin burns. For part B, we need 2 similar properties of visible light and infrared. You could say they are both electromagnetic waves and transverse waves, which travel at the same speed in a vacuum, 3 × 10 to the 8 meters per second. Moving to the next part, the question asks for the differences. On the electromagnetic spectrum, visible light has a shorter wavelength and a higher frequency than infrared. Part C is a calculation. The lamps are 1.5 meters from the car, and we need the time for the infrared to travel that distance. Using the formula speed equals distance over time, we rearrange to time equals distance over speed. So, time is 1.5 meters divided by 3 × 10 to the 8 meters per second, which gives us 5 × 10 to the -9 seconds. Then part D asks us to explain why white paint takes longer to harden than black paint. This is because black is a good absorber of radiation, whereas white is a good reflector. Because black absorbs more energy per unit time, it hardens faster. Question 4 takes us into astrophysics, looking at the evolution of a star. For part A, we need to say what happens to each energy store as the nebula collapses. First, chemical energy store. This stays the same. Chemical energy isn't really involved here. Next, gravitational potential energy store. This decreases. As the gas pulls together, it loses gravitational potential energy. For nuclear energy store, this stays the same. Nuclear fusion hasn't started yet. Finally, thermal energy store. This increases. The gas gets hotter as it collapses, so thermal energy goes up. Part B is a key fact. Whether a star becomes a red giant or a red supergiant is determined entirely by its mass. For part C, we need to discuss the differences between a red giant and a white dwarf. A red giant is significantly larger and brighter than a white dwarf. This is because nuclear fusion is still occurring within the red giant's core, providing a constant source of energy. In contrast, a white dwarf is a stellar remnant where fusion has ceased. While it has a higher surface temperature and an incredibly high density, its tiny size makes it much dimmer than a red giant. Question 5 brings us back to forces and motion, with a spring that obeys Hooke's law. For part A, you need to sketch a graph. You put force on the y-axis and extension on the x-axis. Hooke's law says force is directly proportional to extension, so your graph should be a straight line that passes through the origin. For part B, we have an object suspended from the spring. At the instant it's released, the upward elastic force is 3.2 newtons, which is greater than the downward weight of 2.0 newtons. So, the resultant force is the difference, 1.2 newtons, and its direction is upwards. Next, to find the acceleration at that instant, we use Newton's second law, F equals ma. Rearranging, acceleration equals force over mass, so 1.2 newtons divided by 0.2 kilograms gives us 6 meters per second, squared, also upwards. The last part asks how this acceleration changes as it moves back up. As the object rises, the extension in the spring decreases, so the elastic force decreases. This means the net force decreases, and therefore the acceleration decreases, eventually becoming zero when it reaches the initial rest position. Now, question 6 is all about magnetism. Part A is on the diagram, where you draw arrows on the field lines pointing into the South Pole. Part B asks which material is attracted to the magnet, and the answer is nickel, as it's one of the few magnetic materials. Part C asks how the field lines show the strength decreasing with distance. The answer is that the field lines get further apart as the distance from the pole increases, indicating a lower field line density and a weaker magnetic field. For Part D, we explain why a piece of iron experiences a force towards the magnet. The iron becomes an induced magnet. Specifically, a north pole is induced on the side of the iron closest to the magnet's south pole, and because opposite poles attract, it feels a force towards the magnet. Finally, last question from number 6, explains why the iron isn't a permanent magnet. Iron is magnetically soft, which means it loses its induced magnetism as soon as it's removed from the magnetic field. Question 7 is about a domestic lighting circuit. Part A asks for an advantage of this parallel circuit, and the key point is that each lamp can be switched on and off independently. For Part B, the charged particle that moves in an electric current is the electron. Next, we're told the current in lamp 1 is 22 milliamps. To show its power is about 5 watts, we use the formula power equals voltage times current. The mains voltage is 230 volts, and the current is 0.022 amps, so the power is 5.06 watts, which is indeed about 5 watts. Next question. To find the energy transferred when it's on for 30 seconds, we use energy equals power times time. So 5.06 watts times 30 seconds gives us 152 joules. For Part C, the term voltage is defined as the energy transferred per unit charge. Finally, with switches 1 and 3 closed, the total current from the mains is simply the sum of the currents in those two lamps, 22 milliamps plus 17 milliamps, which equals 39 milliamps. Question 8 deals with refraction. We have 2 rays of light hitting an air-water boundary. Water has a refractive index of 1.33. To explain their paths, we apply Snell's law, N equals sine I over sin r. For ray A, with an angle of incidence of about 36 degrees, the angle of refraction calculates to be 26.2 degrees. For ray B, with an angle of 60 degrees, the angle of refraction is 40.6 degrees. In both cases, the rays bend towards the normal. This happens because they are traveling from air, which is less optically dense, into water, which is more optically dense, causing them to slow down. Question 9 explores air pressure. Part A states that just after sealing the bottle on the plane, the air pressure inside is the same as the cabin pressure, 80 kilopascals. Part B explains why the bottle collapses as the plane lands. As the plane descends, the external air pressure increases, but the pressure inside the bottle remains at 80 kilopascals. This pressure difference creates a resultant force acting inwards, which crushes the bottle. Part C asks how gas molecules exert pressure. They are in constant random motion, and they continuously collide with the inner surface of the bottle. Each collision exerts a tiny force, and the total force per unit area of all these collisions is what we measure as pressure. Question 10. Test your practical skills. Part A is a simple calculation. The weight of a 250-gram load is mass times gravity, so 0.25 kilograms times 10 gives us 2.5 newtons. Next, Part B. In the investigation, the independent variable is the length, L, and the dependent variable is the height, h. Next question. Two control variables you'd need to keep constant are the mass of the load and its position on the strip. Next, we need to suggest how to accurately measure the height, h. The student could place a ruler vertically at the end of the wooden strip and line up the 0 on the ruler with the original height of the wooden strip before the load is added. This allows for a precise reading of how far it has bent down. Next, to Part C. Using the scale diagram, you'd measure h as about 3.1 centimeters on paper, which corresponds to an actual height of 31 centimeters. After plotting the graph of h against L, you'd draw a curve of best fit. Because the graph is a curve and not a straight line through the origin, h is not directly proportional to L, so the student's conclusion is incorrect. Question 11 is about a power bank. Part A defines 1 amp hour. To express this in coulombs, we use charge equals current times time. That's 1 amp times 3,600 seconds, which equals 3,600 coulombs. For Part B, to find the recharge time, we use time equals charge over current. So 3.8 times 10 to the 3 coulombs divided by 2.4 amps gives us 1,583 seconds, which converts to 26 minutes. Next question, ask about using a longer cable. A longer cable has a higher resistance, which decreases the current. Since time equals charge over current, a smaller current means a longer recharge time. Finally, Part C, to see if the 26.8 amp-hour power bank is enough for a week-long trip, we calculate the total charge needed. Device A needs 2.4 amp-hours each day for 7 days, which is 16.8. Device B needs 4.2 once, and device C needs 6.8 once. That totals 27.8 amp-hours, which is slightly more than the power bank can store. So strictly speaking, it's not enough if all devices start from empty, though they might not be fully discharged at the start of the trip. Finally, question 12, analyses of velocity time graph. To find the acceleration at 20 seconds, you draw a tangent to the curve at that point. The acceleration is the gradient of this tangent, which you calculate by doing rise over run. From the tangent, this should give an acceleration of approximately 1.1 meters per second squared. Next, Part B, the distance traveled in the first 80 seconds is the area under the graph. A good way to estimate this is to approximate the shape as a trapezium. Using the formula for the area of a trapezium gives a total distance of about 3,800 meters. Finally, last question. After 80 seconds, the graph shows the car moving at a constant velocity of 64 meters per second. This means its acceleration is 0, so the resultant force on it is 0. The constant driving force from the engine is now exactly balanced by the air resistance, which has increased as the car sped up. Thank you for watching. Education Made Easy with Studia.